Well, first of all, I'd like to thank the speaker for inviting me to give this talk here. So I will talk about the categorified Chern character. And this is joint work with Marco Jahr and Niccolò Sibela. So in the first part of my talk, I want to remind of the classical Chern character. And from then on, focus on some properties that will lead us to what the categorified Chern character should be. In the second part, I will introduce another higher invariant, which is called the secondary Chern character, whose important ingredient is actually to have a categorified version of the classical Chern character. And in the third part, I'll talk about the Grothendieck-Riemann-Roch theorem for categorified Chern characters. Okay, so let me start this talk with some simple examples from topology, representation theory, and algebraic geometry of instances of Chern characters, one of which you might have encountered. So in algebraic topology, if I take M to be a compact manifold, then one instance of the Chern character is a map which sends complex vector bundles on M to the de Rham homology of the space M. And for instance, it sends a line bundle to some of its first Chern class. So this is an example from algebraic topology. If you're a representation theorist, you might be more familiar with this type of Chern character. You take a G to be a finite group. And then the Chern character is the usual character. It sends complex representations of G to functions on the conjugacy classes of the group. And it just sends, if I pick here a module of G, so a vector space with a G action, then it sends a representative of this conjugacy class, let's say G, to the trace of the automorphism that G induces on V by its action. So this is just the classical character of a representation. And most generally, in algebraic geometry, if we take X to be a stack or a scheme, then we have a map that goes from the perfect complexes over X to the Hochschild homology of perf X, which is the same than the Hochschild homology of X. So these are the category of complexes of vector bundles. Okay, so what do this construction have in common? there are three properties. That are important here. So first of all these categories here have a tensor structure, and the Chern character preserves the tensor structure, so it's a multiplicative map. It sends the tensor product of objects to the product of its Chern characters. Secondly, all these categories here have triangulated enhancements. So we can look at the derived category. This is the derived category of complex vector bundles, the derived category of representations over G, and so on. So we have actually a structure. All of these categories have in common that they are structures called distinguished triangles, and distinguished triangles of objects will go to sums of Chern characters. So it sends distinguished triangles BC suspension. So this is sent to satisfies the following. So the Chern character of A plus the Chern character of C is equal to the Chern character of B. This means, in particular, that the Chern character factors to K theory. And thirdly, all of these Chern characters have S1 equivalent refinements. So in the third example, this means that the Chern character factors to negative cyclic homology. Okay, so let us introduce the loop space, which will allow us to give us a hint as to what the categorified Chern character should be, so where it should start from and where it should end, by writing Hochschild homology in a slightly different way. So we'll assume here that X is a derived stack. And we will call X, the fiber product of X along its diagonal embedding, this derived fiber product, the loop space of X. So this can also be written as the internal mapping space in derived stacks of S1 to X, and is denoted by L of X, the loop stack. So what is the connection with what we've just done beforehand? So what is, first of all, the structure sheaf of this loop stack? Well, the structure sheaf of the loop stack is given by the derived tensor product of the original structure sheaf of X, seen as an O of X tensor O of X module. And this means that, therefore, the Hochschild homology of X can be identified with the global section of the structure sheaf of the loop stack. Okay, so we can identify on this side here the Chern character that lands in Hochschild homology, lands in the global section of the loop stack. In the representation theory side, we land in functions on the conjugacy classes of G, but this is nothing else but the Hochschild homology of the group ring CG. Or if you want to see G, if you want to work in this framework, you can consider the stack point mod G, and then you also get this identification of the right-hand side here with Hochschild homology. Okay, so let me draw a table of, it's going to fit here. I should start in the board. So let me draw a table of comparing what we have on the categorified and on the non-categorified side. Let me call this here classical. Oh, hold on, I want this side. The classical side. So here, the Chern character is a character that is an assignment that starts in a stable infinity 1 category, namely prof x. Really, for the Chern character, we will only consider it as an infinity group read because we can interpret Hochschild homology as a space. It ends in O of Lx, the global section of the loop stack, and it factors to K theory. So what would be the categorified equivalent? Well, we want the categorified equivalent to be now an infinity 2 category whose objects are stable, small stable infinity 1 categories. We want them to be tensored over perf x. So we want them to be perf x modules. So this would be going one categorical level up. And to pass from the right-hand side to the left-hand side, you have to consider the endomorphism ring of the unit. The unit of this category is perf x itself. So we land back again on this side here. Now, the structure sheaves of functions on L of Lx, the categorified version of this is quasi-coherent sheaves on L of x. And the categorified version of K theory is a category of non-commutative motives, which I will introduce during this talk. So this is the category of non-commutative motives. And I will explain in which way this can really be thought of as a categorification of K theory. So I can first state the main theorem and then go on explaining the various constructions that appear here. So the first construction of the Chern character of the categorified Chern character goes back to Toen and Vezzosi for infinity group reads, and we have extended this construction to infinity 1 categories and shown some of the properties I will just mention. So there is a symmetric monodal functor of infinity 1 categories. I haven't actually. So I want to denote this category by cut x. If you're familiar with sheaves of categories, you can also think here, can also replace this category by sheaves of categories. This is naturally an infinity 2 category, but I will look at the underlying maximal infinity 1 category, because I want to land in an infinity 1 category, which is Q-core of Lx. So this is the categorified Chern character. And as the classical Chern character, we show that it factors to the category of non-commutative motives. And it has an S1 equivalent refinement, which means it factors to Q-core L of X as one equivalent. So this square here commutes. And also the main properties of the Chern character in the classical case, where are they? Oh, I erased them, sorry. Do hold. So first of all, the first property of the Chern character I mentioned is that it's actually a multiplicative map. Here we have a monodal functor. The second property was that it sends distinguished triangles to sums of Chern characters. Here, in this category, this is not a stable category, so we have no distinguished triangles. But we have a similar structure. We have Verdier localizations of triangulated categories. And indeed, this functor here sends Verdier localizations to distinguished triangles. So really are one categorical level up. So this functor sends Verdier localizations to distinguished triangles. Okay, so now to construct this functor, I will first go a step back and give you the main ingredient of constructions of Chern characters, which is dualizable objects and traces. So there are two main constructions, but both rely on the formalism of traces. So if I take C to be a monodal category, with unit 1, then we call an object dualizable. If there is a dual, so there's another object in C, and maps from the unit to M tensor M dual, which we call the coevaluation map. And dually an evaluation map, so a map from M dual to M to the unit of C, which is called the evaluation map. We want this map to satisfy the following property. If I start off with M, which is 1C tensor M, because M is the unit, I can apply the coevaluation on the first factor and the identity on the second, lands me in M tensor M dual tensor M. So this is coevaluation tensor identity. And I can apply the coevaluation, the evaluation map, keeping the identity here. This lands me back in M, and we want this composition to be homotropic to the identity. So this is what it means for an object to be dualizable. So now if we have an endomorphism of a dualizable object, we can define its trace. A map from M to M, then the trace of F is an object in the endomorphism ring of the unit object of C. And it's given as follows. We take the composition of the unit object, the coevaluation. Then in the middle we apply F tensor the identity. And then we apply the evaluation map. So this is what we call the trace of F. And now the main constructions, in fact, all constructions I know of Chern characters are given. I mean, it differentiates two main constructions. First, by functoriality of traces. So this goes back to work of Keller. And then more recently in the categorical, in the higher categorical world, by Ben-Zvi and Nadler. And the second one uses traces of the monodromy. Which I will also introduce very soon. So this was first done by Chern and Vezzosi. And we also use their construction. And in fact, it is a priori not clear that these two constructions will yield the same Chern character, but one can prove that, which is not easy, that in fact both constructions yield the same character. The advantage in taking the monodromy construction is that we can actually, we don't only have an assignment on objects, but we actually get a functor of infinity one categories, which is something we don't know how to do in the first case, using just functoriality of traces. So let me give you a sketch now of how to construct the categorified Chern character.